Thanks, Srividya. Hello, everyone. My name is Janakiram. I'm a Google developer expert for GCP and IoT. I'm going to walk you through a session on using Kubernetes to deploy and scale microservices. So in terms of agenda, I have an introduction to microservices, a very brief overview of what exactly are microservices, and then we'll talk about how we transition from virtualization to containerization and how containers enable microservices. And because containers are the unit of deployment, we also need to have a platform to orchestrate them, and that's where we have Kubernetes. So I'm going to talk to you about what is Kubernetes and specifically what is Google Kubernetes Engine. And towards the end of the session, I have a live demo where I'm going to walk you through launching a cluster and deploying and scaling microservices. So let's get started. Most of us are familiar with the traditional three-tier architecture, and during the 90s, we have been using this with J2EE, .NET, and a variety of technologies. Traditionally, this architecture had a database backend like Oracle or SQL Server, business logic predominantly written in C#, .NET, Java, J2EE, and then we had UI in the form of GUI or web forms. That was the three-tier architecture. But the challenge with this is when we scale, our unit of deployment and scaling is typically done at an application server level. For example, if we have three components in our three-tier architecture, and one of the components is actually taking the maximum resource utilization, we cannot selectively scale that component. We have to scale the application server, and if the application server is running more than one component, each of those components will also scale. So it doesn't give us a very selective scaling ability, and the unit of deployment is always at the virtual machine or the application server level. So this is becoming a big challenge because we cannot selectively scale the actual components or services that are responsible for handling the traffic or the requests. So the more recent phenomenon has been what is called as microservices architecture. So in microservices, we don't typically have a three-tier architecture. It's a flat hierarchy, and we have multiple services. Technically speaking, you can map a component that you have used in three-tier architecture to a service, but they are slightly different. So in a microservices architecture, we don't go by an application server, which has been traditionally the unit of deployment. In microservices, we have very granular, very well-defined services that do one task at a time. And all these microservices are deployed on a pool of resources coming from multiple nodes or multiple servers that are actually running this infrastructure. And this flat hierarchy and resource pooling gives us the ability to scale the components or services as we need them. In this scenario, you actually notice that we have C3 scaling more than C1 and C2. Let me put this in a perspective. Imagine you are running an e-commerce portal and you're on your big day sale. So a lot of people are window shopping and they want to figure out the pricing before they actually buy, which means the catalog service is what is currently being used the max. In traditional world, scaling up or scaling out the catalog service alone is not possible. But with microservices, you can run more number of catalog services while reducing the number of instances or the footprint of your shopping cart or the other services. And this ability gives us to selectively scale in and scale out the services that are actually in demand. And this flat hierarchy of components or services running on aggregated pool of resources is what is called as the microservices architecture. Let me also spend a little bit of time explaining you the aggregated pool of resources. So what this means is if you are running a cluster of servers and each server has X number of cores, Y amount of memory and storage, the aggregate pool is going to be multiplied by the number of cores, by the overall memory and the available storage. All of them are visible to your microservices application. So they don't specifically target a machine. Instead, they target the pool of resources coming from the cluster or the actual number of resources powering that cluster. So that is at a very high level, the microservices architecture. One of the other important attribute of microservices, excuse me, the microservices architecture is that the services are loosely coupled, as in if you have let's say S1, S2, and S3, these services don't acknowledge the presence of each other. They exist in their own context, but when we connect all of them, they all work in tandem to deliver the functionality. So they are loosely coupled, they are autonomous, and they send messages in a very message-oriented form. This communication pattern makes services highly autonomous and also loosely coupled. Now, how do you package and deploy services? So we touched upon the conceptual attributes of microservices, but as a developer, how do you really write microservices? Because microservices cannot be deployed as a VM, as a unit. They got to be much more fine-grained, they got to be much more smaller in terms of the footprint, and they got to be lightweight. So more recently, we have been witnessing this new paradigm called the lightweight virtualization, which is containers. And containers have become the standard packaging and deployment format. And containers make it absolutely portable in terms of moving the code from one Linux distribution to another. Even Windows actually supports containers. So you can write your code, package it as a container, and deploy it on multiple operating systems with almost no change to your code base. It also brings portability across cloud platforms. For example, if you have your staging, production, and test environments set up in multiple clouds, you can seamlessly move your containers from one platform to the other because they bring the ultimate level of portability. And because containers are directly associated with your code base, that is, every time you commit, there is going to be a CI/CD process, which is continuous integration and continuous deployment, which will result in a new version of a container image. So this is going to make it very easy for you to manage multiple versions of microservices. You can also mix and match different versions of microservices, which are composing of the same application. So that is a brief introduction to containerization. So think of it as a lightweight virtualization built right into an operating system, giving you the ability to deploy and scale applications much more rapidly than virtualization. So let me spend a little bit of time explaining you why we need containers and what is containerization. So software industry is facing the same challenge as the cargo industries of 1960. It might sound very strange, but that is the reality. So when we go back to 1960s, it was extremely challenging to port goods from one location to another. For example, if you had to carry coffee beans with brewery, it was very risky. And similarly, you couldn't mix and match very pungent spices with food grains because one would influence the other. So there was no standard way of carrying goods and also isolating them with the required level of isolation. And once these goods were put on the cargo, they had to take multiple transportation forms. For example, a ship to a goods train, to a truck, to a crane, and ultimately the last mile delivery. Each of them had their own format, each of them had their own form factor and transportation mechanism, and this made moving goods extremely expensive. Now, containers changed the entire landscape of cargo industry. So with container, we achieved a standardization of moving goods from one location to another. And eventually, ships, trucks, trains, and every transportation medium got redesigned to accommodate containers. Today, when the transportation world talks, it talks in terms of containers. How many containers are we moving from point X to point Y? And the industry has agreed on this standard to mix and match different goods and also transport them from one point to another. Interestingly, software world is also going to benefit from the same paradigm of containers. So today, like the cargo industry had challenges mixing and matching different goods, developers have challenges mixing and matching a variety of workloads. Today's application is not a monolithic. It is not one database, one application server, and one front end. We have a variety of components coming together to deliver the functionality of one application. For example, you might have a static website written in Bootstrap running on Nginx. Then you have a dynamic web front end written using Ruby on Rails. Then you have background workers which are doing asynchronous job and they are written using Python, Node.js. And if you're actually doing media encoding, you might be using FFmpeg as your background worker, which is going to encode every input image coming from the static website via the dynamic front end. And then databases are not just relational. We have cache in the form of Redis or Memcache. We have NoSQL databases in the form of MongoDB or Cassandra. Then we have relational databases in the form of PostgreSQL, MySQL, and all these are forming the stack to run modern applications. Now, the challenge is when you take this matrix and try to run it on virtual machines, physical machines, cloud, private cloud, and a variety of environments, it's actually a matrix of hell. You have to make sure that every component works the way it is expected in every environment. And this is going to be a nightmare for developers. So just like the cargo industry benefited from adopting containers, we are going to benefit by moving to containers. So containers are helping us in standardizing, packaging, and deployment. And this is going to bring in extreme parity and portability across a variety of environments. And if you're a developer, you would have heard this umpteen number of times. Oh, it works on my machine, right? And typically when you have a demo to your manager or when you have a client who is actually watching you demonstrate, something is going to fail. And this is the universal paradigm, right? So how do you avoid the paradigm or the syndrome of, oh, it works on my machine? By switching to containers. With containers, you're guaranteed to have the exact same performance and compatibility irrespective of the target deployment environment, which means on a development machine, to your data center, to a virtualized environment, to a private cloud, to the public cloud, it is guaranteed to work exactly the way you want it. And that is the beauty of adopting containers. And now you can see the parallels between the cargo industry and the software industry. So containers make software portable and they are fast becoming the unit of deployment. That is the key takeaway from this discussion. So the other advantage of adopting containers is clean separation of concerns. We live in a world where we have orthogonal goals. If you are a developer, you are rewarded, promoted, and encouraged to deliver more features more often. And if you are an operator or an administrator or a sysadmin, you are actually rewarded, encouraged, and promoted for maintaining stability. But we know that change and stability are two extreme ends. You cannot achieve a balance when you are changing something very often, and it cannot be stable. But thanks to containers, it enables developers to ship more often, add more features, and rapidly deliver software, while enabling ops to actually maintain stability. So this gives us a lot of flexibility in terms of experimenting with new versions while maintaining the required uptime and enabling ops to deliver on that SLA that they have agreed to. So the clean separation of concern is again possible only through containerization. If you're wondering what is the difference between virtual machines and containers and why you should adopt containers, well, if you carefully look at the virtualization architecture, there is hardware, there is operating system, and alongside the operating system, there is a hypervisor. And on top of hypervisor, we have virtual machines. But the challenge with this architecture is every virtual machine is built from the ground up. That means if you are running 4 virtual machines on a physical host, every virtual machine has a redundant copy of the operating system, the runtime, the libraries, the binaries, and the delta is only 10%. But unfortunately, we cannot reuse the 90% of the software layer that is common, consistent, and repeated across multiple virtual machines. And this makes virtual machines very bulky and very heavyweight. When it comes to containers, they don't add an additional layer. Many of the modern Linux operating system kernels come with containers built into them, which means every Linux machine running the most recent kernel is guaranteed to have the container environment, which is called LXC. And by leveraging that, we could extend the ability to run containers almost on any flavor of Linux. And of course, it's not just LXC. There have been a lot of innovations in the world of containers, but at the bare minimum, a Linux kernel is going to support basic containers through LXC. And because there is no additional overhead through hypervisor and we are not redundantly creating VMs running the same software, it is going to be lightweight, it is going to be much faster. So the containers will reuse the underlying host operating system for a lot of capabilities. And only the delta, that is your custom software, is going to be added to the top of the stack. And that's what is going to make your software extremely portable. So when you're actually launching a container, you're not launching a machine that has the operating system, your language runtime, the frameworks, the binaries, the dependencies, but instead you're going to deploy only your piece of software with everything else becoming already available. So containers can reuse a lot of software and a lot of dependencies. That's the beauty of switching from virtualization to containerization. And ultimately, this leads to better utilization. You can run more number of containers on a host machine than the number of virtual machines. So definitely, in terms of resource utilization, containers deliver optimal performance. So this is a visual representation of what I just mentioned. So in terms of VMs, you have physical server, host operating system, hypervisor, and then a lot of redundant guest operating system software, followed by the binaries and libraries that are specific to your application, and finally your application. And when you compare and contrast that with containers, there is no hypervisor and there is no guest operating system that is redundantly copied. So containers offer significantly faster deployment, lesser overhead, and it is easy to migrate with faster start. So data center as a machine. The enterprise data center and even cloud infrastructure is going through a huge transformation. So let's take a look at this new paradigm called data center as a machine. So we have physical infrastructure. That's not going to go away. We are still going to see a lot of bare metal physical servers. And each server is going to be equipped with multiple cores of CPUs, lot of memory, and of course storage. But this physical infrastructure is going to be exposed as multiple virtual machines. And on top of these virtual machines, we are going to create aggregate resource pools, and let's call them clusters. So each cluster has access to a set of resources coming from the aggregate pool. And when you launch your applications as containers or microservices, they are going to be running within the cluster that is nothing but an aggregated pool of resources. And to manage these pool of resources plus your microservices and orchestrate them, we have a cluster manager or an orchestration engine. So the advantage of adopting this architecture is that we are going to get the absolute utilization of the resources. So every virtual machine is going to run multiple containers, and each physical server is going to run multiple virtual machines. And at the end of the day, when you compare and contrast the utilization achieved through virtualization versus containerization, this is going to give you very optimal utilization of infrastructure. So it is not just containers, but we also need to have a new software layer, a platform layer, which is the cluster manager or orchestration engine. And the job of this layer is to coordinate resources, resource pooling, scheduling, controlling across your infrastructure. So that's what is now becoming available to us as Kubernetes. So Kubernetes is that cluster manager responsible for orchestrating your deployments in a pool of servers. So Kubernetes came from an internal Google project called Borg. Google for more than a decade has been running containers, and they have been managing containers through an internal orchestration tool called Borg. 5 years ago, Google has open sourced a part of Borg and called it as Kubernetes. And Kubernetes is now becoming the new data center operating system. Now, what I mean by that is you don't need to deal with one machine at a time, but you treat your entire data center as a machine. And when you are looking at your data center as a machine, you need an operating system that can cut across all the virtual machines or physical machines. And that software, that distributed operating system, responsible for managing all your servers in the data center or your cloud infrastructure is Kubernetes. It is a distributed operating system responsible for running modern workloads packaged and deployed as containers. And the piece of code that you run in Kubernetes is called as a microservice. So now everything starts to make sense because we have code packaged and deployed as containers, and containers run in VMs or bare metal servers, but Kubernetes is that software that handles the orchestration across your applications and the underlying infrastructure. So it is the new operating system. Just like Linux manages your hardware resources running on your machine and the processes running on the top, Kubernetes manages containers at the top and infrastructure at the bottom. And that is a very critical layer to run modern infrastructure and modern applications packaged and deployed as containers. So Kubernetes exposes unified API, and using this API, you can submit requests to Kubernetes to schedule your microservices. It decouples applications from machines. For example, you never have to worry about which machine is going to run your microservice. When you submit a microservice to Kubernetes, depending on the runtime context and the utilization of the infrastructure, Kubernetes will intelligently place your microservice in one of the virtual machines or physical servers. So this is going to effectively decouple your code from the underlying hardware. It automates application configuration through service discovery. One of the biggest challenges of running distributed computing is service discovery. How does service A discover service B, and how does service B discover service C? Because all of them are running in their own world inside their own context. So Kubernetes makes it extremely easy for services to discover each other. And this is going to make it very easy for us to create loosely coupled applications without writing a lot of plumbing code to just make service discovery happen. And it is built right into the platform in the most seamless form. Kubernetes manages the overall health of the cluster, all the way from the machines that are actually exposing the underlying hardware to the application that you have deployed and other dependencies. It can maintain and track the health of the entire stack. And at any given point of time, if something goes wrong, Kubernetes can do self-healing. For example, if your desired configuration is to run 10 instances of your web application, and for some reason, if 2 of the instances are killed, Kubernetes can bring back those 2 to ensure and maintain that the desired configuration is still 10 instances. And that gives us a lot of power in terms of maintaining the desired configuration without doing a lot of configuration or plumbing. And because we are dealing with lightweight containers, we can do a variety of things. For example, blue-green deployments. Deploy version 1 and version 2, run them in parallel, see which one works better, and automatically promote one of the versions. That is called blue-green deployments. And with Kubernetes, this is absolutely simple. You can also do what is called as canary release. So canary release is basically deploying multiple versions of your software in a very controlled environment and closely monitoring them and gradually increasing the footprint of your versions. So for example, you can run V1 and V2 in parallel, but initially send 10% of traffic to V2, see how they perform, make the traffic go up to 50%, and then eventually terminate V1 and run V2 100%. So that is called a canary release. And this is again possible through Kubernetes API and the way the software is structured in this modern infrastructure. So let's take a closer look at Kubernetes. First thing, the terminology and the concepts. Kubernetes deals with containers. Your software that you're writing got to be packaged and deployed as containers. And the container is wrapped inside what is called as a pod. A pod can contain one or more containers. So if you have a combination of containers that need to work together, for example, a web server and a cache server, and every time the web server is pulling from the database, it checks with the cache, and the cache server and the web server need to go together. So it makes more sense for us to package the web server and cache as one pod. So a pod is a wrapper on top of containers, but it may contain one or more containers. A replication controller is the way we scale pods. So when you actually say, Kubernetes, run my web application at the minimum 10 instances, right? This declaration is actually defined through what is called as a replication controller. And replication controller is an instruction to Kubernetes to ensure that at any given point of time, we have those many pods running as defined in the declaration. So labels. So labels is what makes a service discovery happen. Labels or annotations will create metadata on Kubernetes objects through which one object will discover the other. For example, you have a load balancer and you have a set of web pods. How do you make sure that the load balancer drives traffic only to a select subset of web pods? Well, by defining some labels and creating an association with the load balancer. Services are how we expose pods to the outside world or even internally. So a service is like an entry point to a set of pods. So if you have, for example, a MongoDB pod running inside Kubernetes, you create a service through which your web pods can talk to your MongoDB. So typically we have pods and a service treated as one unit, as a microservice. Nodes are the host machine running within the cluster. In the previous generation, they were called the minions, but worker nodes are basically the workhorses of Kubernetes, where the actual containers will end up running. That's where your application instances will get scheduled. Finally, cluster. It's a collection of nodes, and it's going to aggregate the pool of compute, storage, and network resources. Let's take a further look at the architecture. So at a high level, Kubernetes is not very different from other distributed computing environments. You have a master, which is the control plane, and then you have multiple nodes. Nodes are stateless, as in they can come and go, but the master is going to maintain the entire health of your cluster. A master runs the control plane while the nodes run your actual workload. Clients talk to the master. For example, if you want to deploy a web application, you're going to submit the job to the master, and the master will figure out which node or set of nodes will end up running your application. So you always talk to the master, and the master will control, schedule, and manage the rest of the infrastructure as well as your application deployment. So what really goes into a Kubernetes master? Let's dissect it. So we have Docker, or the container runtime. This can be runc, which is more generic, more broader container runtime. There is something called a kubelet, and this is going to be responsible for maintaining the communication. This is optional to be running inside the master, but it is an essential component. Then we have a proxy responsible for routing the network traffic and also enabling service discovery. Then we have other components like a scheduler, and scheduler is like a coordinator. It can basically take your request and can figure out which node is going to run your microservice. Controller is going to maintain the desired state of configuration at any given point of time. etcd is a distributed key value database, and it is going to act as a single source of truth. At any point of time, you can query etcd to figure out the state of your cluster. So it is going to maintain the entire state of your cluster, of your workloads, and everything related to the cluster is going to be made available within etcd. It's a key value in-memory distributed database. And then we have an API server, which is responsible for accepting the request coming via the REST endpoint and then cascading it all the way down to the node. So that is how the master is architected. The most important aspect to understand here is that it's the control plane, and the control plane has an API, and the clients will only talk to the API. And from API, it goes to the scheduler, the controller, and all the way to the node. Similarly, when we dissect the Kubernetes node, of course, we have the Docker, which is the container runtime. It could be any other equivalent container runtime. Then we have the kubelet. Kubelet is like the agent, which is going to call home, in the sense that it's going to maintain communication with the master by telling the current resource utilization and the health of the node. So kubelet is the agent, which is going to be the conduit between the node and the control plane. Then we have a proxy. Proxy is extremely critical for us to maintain the communication, the service discovery, and the entire network routing. Then we are going to deploy multiple pods. And because this is a node and it doesn't need to run the control plane, we free up all other resources and maximize on running the workloads defined and deployed as pods. And what is a pod? It's a collection of containers, one or more containers. So we are now going to switch to a demo. I'll walk you through all the steps required to launch a managed Kubernetes instance running inside Google Cloud Platform. And the scenario is pretty simple. We are going to deploy a to-do application as a set of microservices. So the persistent layer is going to be running inside a MongoDB. That's the database pod. Then we have the stateless web application, which is written in Node.js and Express. That's going to be deployed as a set of stateless pods, and we call them as the web microservice. We are going to launch a load balancer, which will route the traffic to one of the web pods, and the web pod will talk to the backend MongoDB database. Again, this is not a three-tier architecture. It's running in a flat namespace. It's running in a flat hierarchy where MongoDB is running alongside the Node.js Express application. So it's not really a three-tier application. That is the key thing here. All right, so let's take a closer look at GKE, Google Kubernetes Engine. If you have an active account with GCP, you can go to your dashboard, click on Kubernetes Engine and clusters, and this is going to bring up the create cluster dialog. And here you can give a name. For example, let's call this to do demo. You can create clusters of type zonal or regional. A regional typically spreads your nodes across multiple zones, but it is okay to launch a zonal Kubernetes cluster if you don't want to spread your resources across multiple zones. So it's going to run within one zone, and then you can choose the zone. Google Kubernetes Engine is one of the managed services, the first managed services to become available in Mumbai. So you can choose Asia South 1, and this is going to launch a cluster in Mumbai. And the latency is extremely low when compared to other locations. So if you are running workloads from India, I strongly suggest you consider Mumbai as your region or zone. And then you can choose the master version. There is backward compatibility. You can choose from a variety of versions, but the default is 1.11.7. So go for the default one and then give the number of nodes. So by default, it is 3 nodes. You can leave it as it is, but customize your machine type. So depending on the workload, you could choose how many vCPUs you need and what is the memory and so on. You can also use a custom machine type if you really want to, but go for the default one if you are not running production workloads. So this is good enough. I'm choosing 1 vCPU with 3.75 GB of memory, and then I'm going to click on create. Pretty straightforward. And once you click on create, this is going to launch a cluster. Now to save time, I have already gone ahead and launched the cluster. So you see this cluster called to do demo, and here we can see the number of nodes. For example, when you click on nodes, it shows that there are 3 nodes. If you want to connect, you can always click on this connect button, and it gives you the command line parameters to basically get your credentials into your local machine. So now I'm going to copy and paste this and then run this in my terminal window. So this is going to fetch the credentials and the metadata associated with the Kubernetes cluster. Now we can verify this by running what is called as kubectl. Kubectl is the CLI to deal with the control plane or the Kubernetes master. I have already installed. You can actually look at the documentation on how to install kubectl. So I have kubectl get nodes, and this is going to list down all the nodes. So here we see that there are 3 nodes in this pool, which is basically the cluster. And now I want to show you a very simple application, right? So here you basically have the database pod, and if you notice, we are actually launching MongoDB, exposing port 27017, which is the default port. And to expose this to the rest of the world, we actually create what is called as the database service. And because we are exposing this internally, we call it cluster IP. Cluster IP is internal to Kubernetes so that the web pods can discover the MongoDB pods. Then we have the web replication controller. So a replication controller or replica set will make sure that at any given point of time we have at least 3 replicas, and this is how we scale microservices. And because we are saying we need at least 3, Kubernetes will ensure that the consistent number of pods is always 3. If for some reason one of the pods gets knocked off or gets killed, Kubernetes controller will automatically bring back the other pod to maintain the count of 3. So that's what is called as a replica set. And then to expose the replica set to the outside world, we create the service as type load balancer. And this is the key thing to understand. Cluster IP is exposing MongoDB within the Kubernetes cluster, not available to the outside world, whereas the web microservice is exposed to the outside world via the public load balancer. So we can directly hit the load balancer, and that talks to one of the web pods, and web pods will talk to one of the database pods. So that is the hierarchy. So that's about it. If you are looking at this for the first time, don't worry, this is very simple to get started. The definition that you are seeing here is actually called as YAML. YAML is the declaration protocol that we actually use. It's the markup language to declare Kubernetes objects. And once we have all of them in place, we go ahead and apply them. So I'm again going to use kubectl apply all my artifacts. So I run this, and this is going to, oops, let me be inside deploy. All right, so I'm going to now run kubectl apply -f dot. So basically what this does is it picks up all the YAML files in the directory and automatically creates the associated objects. So first we create a MongoDB pod, then we create a service associated with the MongoDB pod. And this service is enabling the web pods to talk to the MongoDB. If you remove the service, then the pods become obscure. You cannot even reach them. Then we create the replica set for web, because we are running multiple replicas of the pods. That's why it's called a replica set. And then we expose the web replica set to the outside world. This becomes clearer when we actually run kubectl get service. Now you notice that there is a cluster IP for database. For web, the external IP is still pending, which means the Google Cloud Platform is now creating a load balancer and very quickly associate that with the web pod. So let's just give it another, there we go. So now we notice that there is an external IP associated with the web service. Now I can actually launch this, and we should now see a very simple web page. So this is going to show us the simple to-do list application. So while this is coming up, the load balancer is still being created. I can actually describe the service called web. Oops, let me get this right. So so now you notice that this is the load balancer ingress, and this has an IP address. And if you actually go back and check the GCE load balancer, you'll notice that there is a new load balancer that is created and associated with your web pods. Similarly, when you actually introspect the database service called DB, it shows that it is a cluster IP, and the cluster IP is available only within the cluster. Okay, let me get this right. Let's look at services in the dashboard. Okay, there we go. So now we have the to-do application. So let me add a to-do, finish the demo, right? So when I actually add this, it gets persisted in MongoDB, and you can get this done. So click on this, and then it gets deleted. So it's a very simple microservices application consisting of two microservices: the MongoDB NoSQL database as a microservice, and the Node.js Express application as another microservice. And we simply connect them together through Kubernetes infrastructure, and we have gone live. Now let's also do what is called as kubectl get pods. So now it's not surprising to see that there are 3 instances of the web app and 1 database instance. We cannot scale database because we are actually running a persistent stateful workload, and we can only have 1 instance at any given point of time. But guess what? I can actually run multiple instances of my web app with just 1 command. So kubectl scale replica set called web, and number of replicas is 6. So this single command will basically take our pods and replicates them to run 6 instances. So we already had 3, now it is actually launching another 3. So now we have 6 instances of web pod running there. So let me put this in watch mode, and very soon we'll actually notice that we'll have 6 instances of web pod and 1 instance of database. So when you actually hit the load balancer, Kubernetes will automatically route the traffic to one of the pods. And this is how you can actually scale. Once you are done, you might even want to scale it down. So kubectl scale replicas to 2. Now this is going to terminate some of the pods to bring the count just to 2. So now you'll actually notice that 4 of the pods are getting terminated. When compared to VMs, scaling this is extremely fast. And if you carefully look at the infrastructure utilization and optimization, this is going to deliver the maximum utilization of the underlying resources. So you can very quickly balance your cluster by running the optimal number of pods required for your application. So this is Google Kubernetes Engine. Now, by no means this is like a deep dive, but my objective is to give you a quick introduction to microservices, containers, the role of Kubernetes, and how to get started with Google Container Engine. So that brings us to the end of this session. Thanks for watching this, and stay tuned for the next session. Over to Manohar, who is going to deliver the next session. He is the trainer for rest of the day.